Okay, this video is our second video that is a preview of AP Statistics, and we're going to talk a little bit about the normal distribution here, the normal model, and also a little bit about linear regression. Of course, in the school year, we'll cover this more thoroughly. It's just designed to introduce you to to these concepts. So hopefully this will help out and make some sense to you. And so the first thing a normal distribution is, and in the first video we talked about distributions of quantitative data. In other words, when you graph them, a lot of times when you graph a distribution of quantitative data, so something like people's heights or people's weights or just anything that is in essence sort of a number, the miles per gallon for a car, or the heights of trees, or the number of fruit and trees, that sort of thing. When you graph it, a lot of times there's a center to it, the mean, the average, and most of the time it's going to be around that average. But sometimes, but not that often, it'll be kind of far away, and it'll have this bell-shaped symmetrical curve like this that you may be somewhat familiar with, which we call the normal curve. And the reason it's called normal is because it occurs a lot. And so we want to be able to make calculations with it using this table right here, as a matter of fact, and using our calculator. So a lot of times we really like it when things vary normally, as we say. In other words, when we look at all the different points, they look like that. And so we've got to be able to make calculations using this. And so in this case, in this context, it says the test is given to a large number of students to measure their knowledge of American history. The scores on the test vary approximately normally. In other words, it looks like that bell-shaped curve we just talked about. And it has a mean of 82 and a standard deviation of 4. The standard deviation, in essence, means the average amount that the points vary from the middle. It's the average amount that it's off. In other words, the average score was 82, but it wouldn't be that unusual at all for someone to get one standard deviation above the mean, which would be 86, or even 2 standard deviations above the mean. But anyway, so it says draw the distribution of scores. So it says the mean is 82. So right in the middle is 82. So I'm going to try to draw. You don't have to be a great artist like this, but just draw a mound-shaped symmetrical curve like this that goes like that. Technically, it never does touch the x-axis, but it gets really close to it once you get it beyond about 3 standard deviations. And so the middle of this thing is 82. Now, when it says sketch the distribution, I'm going to label it as normal. We're going to work with a number of different distributions this year, and always label your distribution. 1 standard deviation to the right is going to be basically halfway down this hill at what we call an inflection point. It's where the concavity of the graph changes, but that's not important. What is important is basically halfway down this hill is going to be 1 standard deviation. So a standard deviation is 4, so that would be up here at 86. 2 standard deviations is going to be basically right here. So that'll be 4 more, so that'll be at 90. Okay, now let's go 2 standard deviations below the mean. So halfway down this hill on the left side is going to be 1 standard deviation below it, so that'd be 78, and then 2 standard deviations is 4 points below that, which would be 74. And so that's a well-labeled curve where you've got the mean, you got 1 and 2 standard deviations above and below the mean. And you'll notice that once you get beyond 2 standard deviations, there's not a lot left. As a matter of fact, there's going to be roughly what we would call 5%. And then 3 standard deviations is there's almost nothing out there. In fact, 99.7% of the normal curve is within 3 standard deviations. But anyway, so that's in essence drawing the curve. All right, in order to make calculations on a normal curve, we've got to be able to find a z-score. A z-score is just the number of standard deviations your score is from the mean. So a z-score is the number of standard deviations this value is from the mean. Okay, that's what it is. Our formula for z-score is just x, whatever the value is. In this case, this guy got an 89, minus the mean, which we're going to call mu. So sometimes it can be mu or x bar. Mu is if it's of a population, x bar is of a sample. We'll talk about that later. And then the standard deviation we call sigma. And if it was a sample value, we call it s. So sometimes you'll see this written as x bar and s, but they're basically the same thing, mean is standard deviation. So to find the z-score that Sven got, so you'd say his score was an 89, The mean was an 82, and the standard deviation is 4. And so that would be 7/4. So his z-score is 1.75. So that is his z-score. So he is 1.75 standard deviations above the mean, that's well above the mean. He did well, he did really well relatively. So you find the z-score. Now this is what percent of people did Sven score higher than? In other words, what is his percentile? So this is an important ranking for us in the world of stats. What percentile are you at? In other words, what percent of people did you do better than? And so, all right, I'm going to show you a couple of different ways to figure this out. First of all, with the table, and you do need to know how to use the table, and I'm going to show you how to use a calculator. So you'll be given a table like this. This is our standard normal table, and so it has a normal curve, and this standard normal curve, the mean of this is 0, and the standard deviation is 1. And what this tells us areas that are to the left of a value. In other words, it tells us the percentile. This probability here, in essence, this area represents percentile. It represents the percent that is to the left or lower than my score. And so what we would do is, you notice on the left side here, it has z-scores. And notice it has the ones place and the tenths place. And then up top is actually the hundredths place. Okay, and then all these values in here are this probability, this left area. So it is telling us exactly what we need. We need to know the percent that did less than our z-score of 1.75. And so, well, this page of z-scores is negative. I mean, in a normal curve, half of the z-scores are going to be negative. So it just means your score is below average. So I'll just go to the next page. The next page has z-scores that are positive, which is going to have a percentile, greater than 50%. And so we would go to, we're going to 1.75. And so we would go to notice we go down here to 1.7 and then go over to the 0.05 column. That's our hundredths place. And so we'll see where these two intersect. And so they intersect 1.75, I believe, right there, 0.9599, 0.9599. And so that's what this is. So that is 0.9599. In other words, about the 96th percentile. So if you get 1.75 standard deviations above the mean in the normal curve, you're scoring about the 96th percentile. He did better basically than 96% of people. By the way, if like, let's say your value was a little off, like let's pretend it was 1.752, you would just estimate it as best you can. You go to 1.75, and then you go 1.752, maybe a little bit more than that. So it would be somewhere between there, and you could estimate it, and that's fine. It doesn't have to be exact. So that is how you would use that table to find that. Now, the other way to do this is to use what is known as normal CDF. And yes, you do need to know how to use the table, but you could use normal CDF to find this. And so we'll use normal CDF to find, if we have a z-score of 1.75, what is the percent that's below it? Now, normal CDF stands for normal cumulative density function. All right, it is a density function is basically this thing here. So it's a normal cumulative density function. And so this is the way we access it. It's under our distribution menu, which is above the vars button. And so if I hit the second button, go second distribution, so here's our distribution functions. We will never use normal PDF, by the way. We'll use normal CDF, all right, like this. And I need to know, this is telling me this area. This is telling me this probability or the area that is to the left of my value. And so I'll hit enter on that. And so I need to know everything that is less than 1.75. So notice, the lower value, in essence, of this curve, so I'm looking for this area of this curve like this, and we're up here at 1.75 for our z-score. I need to know this area. And so the left bound, or the lower bound of that, is negative infinity. And so, of course, it set it there automatically. But if it didn't, so make sure and don't hit the minus button. Hit the negative button, which is below the 3. So you hit minus, and then if you want to, you can just hit minus like 9 billion or whatever. And that's effectively negative infinity. Realizing when you get beyond like negative 3, it's almost touching the x-axis. So it's really close to the x-axis there. My upper value is 1.75. And then my mean is 0, standard deviation of 1 for a standard normal curve. That is, mu is my mean, sigma is my standard deviation. And then I hit enter. And there we go. And so, of course, that's the value we got off of our table. Or what you could do is this. You could, from the very beginning here, you could just enter this mean and standard deviation as opposed to finding a z-score. So what you could do, second distribution, normal CDF, and then go negative infinity, and our value was 89. That is his score. Our mean is 82, and our standard deviation is 4. So that's without finding a z-score, which is most of the time that's probably the way we're going to do it anyway. And so we would hit enter, and that would give us the right answer. Now, what about showing your work on something like this? So showing your work on a problem like this, you would just write normal CDF, and then my lower bound was negative infinity, so that's negative infinity. My upper bound was 89, my mean was 82, standard deviation of 4, and it's important to label what these things are. So I'll put an LB for lower bound, UB for upper bound, mu, and then sigma, okay? And so that would be, in essence, showing your work. Now, of course, just like I've done here, you could be asked to draw the curve and define the z-score. So make sure you understand how to do that. All right, so now let's look at this. So number 4. One student's score was less than 10% of scores. Now let's think about this, less than 10% of scores, like that. So in other words, there was 10% of scores that were bigger than that, 10% of scores that were bigger than that. So there was 90% that were less than that, all right? So what we can do is we can use a function called inverse norm. So normal CDF tells us the area of the curve. But inverse norm tells us the x value here. Okay, so what we will do is we'll use what is known as inverse norm for that when we're given, in essence, a percentile. So I will do second distribution and go to inverse norm. And I like always using the left area. And the left area here is 90%. Now, it's the percentile. So I'll go 0.9. And then our mean of our curve is 82, and our standard deviation is 4. Left area. And so that would be 87.126. So 87.126. Showing your work on this problem, you would write inverse norm. Our left area is 0.9, so I'll write left area. Our mean is 82, standard deviation of 4. So there's our mean and our standard deviation. That would be showing your work. Okay? Now, without using a calculator, what you would do is you would go in the exact opposite of what we did with the table up here. And so we will find where the 90th percentile is by looking in this table. Well, where's the 90th percentile looking in this table? So we'll look as close as we can for 0.9. So for 0.90, and we'll estimate it as best we can. And so, well, it's somewhere between there and there. So it's somewhere between there and there, kind of closer to the left-hand side. So when you look at the z-score that goes with that, it's 1.28 and 1.29. And so 1.28 is closer, so I will use that. And so we would use our z-score of, so finding this with our z-score, we would say, well, my z-score is 1.28, and then we'll use the z-score formula. That is x minus 82 over 4. And so used to, before we had these calculators function, this is what we would do with all of them. And so we would say, okay, so I'll say 1.28 and then just use my algebra skills, go times 4 is equal to, and then plus 82. And so we get 87.12, which is pretty close to what we got there. So that is how you do it by hand. Okay, that is your introduction to the normal curve, that's most of actually what's going to be in chapter 2 in your book. And so now I want to give you a little preview of chapter 3, which is linear regression. Now, linear regression occurs when you have two quantitative variables, and we want to see how one variable is related to the other. Previous to this, in chapter 1 and chapter 2, we would just look at one variable. But what's interesting to us is how, when one variable changes, what happens to another. In other words, let's say when someone takes medicine, how does that affect their blood pressure? Or how does the amount of fertilizer affect the size of the tomatoes? Or in this case, how does the amount of study time affect test score? So we like seeing how two variables are related. When we change one thing, does that make something else better? And if those variables are quantitative, then It's what we call a linear regression situation. So the first thing we're going to do, well, let's look at this context here. So a teacher wishes to see the relationship between the amount of time that students study for a test in hours and the score they get on that test. And so there's our data there. And so we would notice, well, this is two variables, this is paired data, that goes with that goes with that, and so forth. So this is a linear regression. Our graph in this situation is what we call a scatter plot. It's just an X and Y graph. And so what we would do, and is we would just, doesn't have to be perfect, just draw a rough sketch. And so our study time is what we call our explanatory variable. It's our X variable. So our explanatory variable, our X variable, study time, it goes from 0.1 to 2.2. So if I go, so I'll like say, like this is 0.5, and this is 1, and this is 1.5, and this is 2, and this is 2.5. That would cover all the data. And so this is study time in hours. Make sure to label and scale both of your axes. And so that's our study time. And of course, our response variable, as we call it, is the test score. So the response variable is your Y variable. So that's explanatory, that's response. And so in our response variable are going, let's see, the low score is like, it goes 71 to 91. So if I go like 70 and let's say 80 and 90, let's say, like that. And then you just plot your XY coordinates. So 0.1 is at 74. So 0.1 is at 74. 0.4 is at 71. And then 0.6 is at 75 and so forth. And we're making what we call a scatter plot. 0.7 is at 83. So 0.7 at 83. 0.9 is at 81. So 0.9 is at 81. 1 is at 84. And then 1.3 is at 88. 1.3 is at 88. 1.7 is 85, so 1.7 is 85. 2.1 is at 86, and then 2.2 is at 91. 2.2 is up here at 91, and so there we go. And so that's all there is to a scatter plot. Describe it, all right? When you're describing a relationship between two quantitative variables. Now, when you describe, if it was just one variable, like we did in Chapter 1, in that first thing, we would cuss. Describe its center, unusual value, shape, and spread. We got two variables here. And so we follow the acronym DOFS. Follow the acronym DOFS. It's direction. And its direction is, in general, is it going up from left to right, or is it going down? And if it's going up, we say it's positive. In general. Now, it doesn't mean it's positive for every point. It means, in general, it's going up from left to right. Certainly, it's negative a lot of times in 82 points. There to there, but in general, it's positive. All right, are there any outliers? Now, outliers in a regression setting is anything that is way above or way below the line. And there's none, now we're going to create a line here. In other words, outside of the pattern in the vertical direction. So way above or way below the other points. And there doesn't appear to be. All right, it's form. And basically, is it linear or not? And there's really sort of two main options we have. Form is either linear or it shows a noticeable curve, like some form of parabola or exponential or something like that. And we'll talk about that. But in this case, we would say it looks pretty linear. In other words, it looks kind of scattered about a line, maybe a bit of a curve there, but we'll talk about that later. And then lastly, how strong is it? In this case, we would say it is very strong. It is, in other words, it's tightly packed to a line in essence. And so that is drawing a scatter plot and describing it. Is it positive or negative? Are there any outliers? Is it form? In other words, is it linear or is it a noticeable curve? And how strong is the relationship? In other words, how tightly packed it is to a graph. Now, we're going to create a line of best fit that is called a least squared regression line. And I'll show you how to do that with your calculator in a minute. But in this case, it's given to us. That is, in essence, a line that is going to go roughly through this data that we can use to make predictions. And we can say, hey, if someone studies this amount of time, what's their test score? All right, so in this case, it was given to us. So there is our line. So if someone studied 3 hours, what score would you expect them to make? Now, our X variable, our explanatory variable, is study time. So this just means plug in 3 for X. So this would be 73.19 plus 7.829 times 3. And when you do that, you would in fact get 96.9 6.677. So that is our predicted score for them based on this model. Now this, by the way, we plugged in 3, and 3 is outside of the domain of our x values, and so we would call this an extrapolation. And extrapolation should always be viewed with caution. In reality, these models should only be plugged in for values that are inside our domain of x values. So anyway, and so if you do, you don't say necessarily it's wrong, you just say it's an extrapolation, it should be viewed with caution. All right, and then you could plug in the other way, plug in 79 for test score. Well, test score is my response variable, so that's y. And so we would say, well, 79 is equal to 73.19 plus 7.829 times x, and you solve that for x, and you get 0.742, and this one has a units, and so that's hours, however many minutes that is, but we can just leave it just like that and solve it like that. Anyway, and then lastly, what is a residual? A residual is how far above or below the line of point is. So this particular point, 2.186, which is this point right there, so that point is here. How far, when it says what is the residual, how far above or below the line? In this case, how far below the line is that? And so we want this distance. And so the way you can calculate a residual, this is the way it can be calculated. It is just the actual y value. It's the actual y value minus the predicted y. Minus the predicted y value. Now the actual y value of that point is in fact 86. What do I mean by predicted y? It's the y value on that line. So what you would do is you just plug in your x value, where the x value is 2.1, and I'll plug it into my equation. So this would be 73.19 plus 7.829 times 2.1. Like that. And so when you calculate that out, it ends up being 86 minus 89.6309. And that in fact is negative 3.6309. All right, that is the residual. That is how far our point is below the line. And so residuals, in essence, what they do is that when we look at residuals, it tells us how off our line is from our actual points. And so they're going to be important issues for us. So that's how you find a residual. And that's it. That's it for this video. That's your preview of Chapter 2 and Chapter 3. I hope it was helpful to you. Thanks for watching. And we'll see you on the next video.